Okay, so welcome to week 2 session. So we'll start with your questions which you asked me last time. Okay, am I audible to everyone? Yeah, okay. So I think there was some question about stationary gas analysis and moving gas analysis, isn't it? Yeah, so it's nothing, it's just it's what you know exactly. So last time you have defined for me. So let me just explain to you what exactly is it. Okay, so now let us consider we have this flow in a pipe or between two plates. Okay, and let us say you have this piston. Okay, and the piston is being pushed towards this air which was initially stationary. Okay, so this air was initially stationary. Now what you do is you give this piston a push, so it is going to push all the gas particles in front of it forward, right? So you have introduced a perturbation to the flow over here, and that perturbation is going to be carried forward. So understand that the perturbation in a fluid is not carried just by one particle's motion. What happens is this particle will go and push another particle, that will push another particle, and so on, and the perturbation itself will move with the speed of sound, right? So a wave front is going to be created, and this wave front is going to move forward with some speed c, and the piston itself you had perturbed and moved it with some speed v. So now if I draw the path, so what I'm going to draw is t versus x, right? And x is along this plate or along this horizontal direction, and let us say at a particular instant, let us say that this is my position of the wave front, right? So how did this wave front come over here? The perturbation must have started at some time. The perturbation started at some time, and that traveled to this point, isn't it? Do you understand this? Yeah, exactly. This is displacement time curve itself, right? So instead of having x versus t, I'm having t versus x. Okay, and how will this piston move? The piston is also going to move forward. So it started at some point, at this point, and it is also going to move forward. Now the question is, will the piston have the same motion as this perturbation? No, because the perturbation will travel much faster in the form of the wave, isn't it? So what is the speed? The speed is dx by dt. And what have we plotted? We have plotted t versus x. So that is over here, this slope is dt by dx, right? So if I am saying that the speed of this perturbation is higher and the speed of the piston is lower, then the motion of piston is going to be like this, isn't it? The slope is going to be dt by dx will be more, so dx by dt will be less. V is less than c, right? Is this part clear? Yes. Yeah, this is for moving gas analysis. I will come to stationary gas, but this part is clear, right? Okay, so now this is moving gas analysis means what? I am looking at the gas when it is moving. Okay, now I will do a stationary gas analysis which says that I am going to look at the gas from a frame of reference from which it will look stationary to me. So I am just changing my frame of reference. Are you understanding? Yeah, so what I'm saying is that right now in this moving gas analysis, so this I'll write is your moving gas analysis. You are seeing the gas as it is moving, because see, you are sitting over here. I'll draw your frame of reference here, in the lab or in this it is fixed location, and the piston is moving and the gas is also moving forward. So you are looking at the gas as it is moving. Clear? Now if I basically go and sit on this wave front, then what will I see? The gas particles on this wave front will be stationary to me, right? Just exactly on this wave front. Yeah, so you will be moving forward with a speed of c, and you will see these particles with respect to you. So now if you are sitting over here, you can't see this c speed, right? So I'll just delete this, and what you can see is these particles are moving in the opposite direction with speed c, and this piston is coming close with speed v. So with respect to you, it is actually moving away with a speed of c minus v, right? So that is what you draw on your curve now in your t versus x. So that is why the slope in this graph becomes negative, because now the speed is negative, isn't it? Is this clear? If you don't understand this moving gas, stationary gas analysis, you just see it like this. There is one frame of reference which is stationary. Okay, so with respect to that stationary frame of reference, you will see the gases moving and you will see exactly what is there. But if you put your frame of reference onto the moving gas, then you will see the gas is stationary. And your frame of reference will define certain quantities, especially the speed of the gas, the speed of this piston. But okay, now I'll ask you a question. Will it change the temperature or the pressure of the gas? How will it change the temperature? No. So no, I'm not saying that the velocity of the gas is being changed. I'm saying your frame of reference is changing. So whether you are doing frame of reference will not change anything about the temperature or the pressure. Okay, so these are called the static quantities. So I'll just write this down for you. So there's something called static quantities, and these static quantities do not depend on the frame of reference. Okay, what depends on the frame of reference? Sorry, dynamic quantities like enthalpy. Why will enthalpy depend? What is the formula for enthalpy? Stagnant. Okay, so it not just enthalpy, all the stagnation quantities. All the stagnation quantities will depend on your frame of reference, isn't it? Okay, so can you define for me what is say stagnation enthalpy now? Completely to rest. So you are saying that stagnation enthalpy is when the flow has been brought to rest. Is that all? Isentropic, not adiabatic. Yeah, so that is isentropic, right? Adiabatic plus reversible, we saw last time itself, it is isentropic. So why do we want to do this? Why do we even calculate something called stagnation quantities? Yeah, for a reference. So basically what we do is, let us take a fluid which has some quantities, temperature, pressure, density. And like we said, it does not depend on the frame of reference. So we don't care about what is the speed and so on. But now if I have to analyze the amount of energy in this flow, then it's not just these static quantities which define the energy of the flow, even the velocity defines this energy, right? So the frame of reference through which I calculate these stagnation quantities will actually define that stagnation values. Okay, so if I were to calculate the stagnation enthalpy sitting in the frame of reference of lab, then I'll bring this flow completely to a stop. But if I was sitting in some other frame of reference, which is say moving at some speed s, then I will bring this flow to a speed s. So it is not necessary that you have to bring it to a speed 0. Okay, so one of you said that stagnation quantity is when you bring the flow to a stop. No, it has to be brought to a stop with respect to your frame of reference. Okay, is that part clear? Yeah. Okay. Okay, so yes. So in stationary gas analysis, what I explained right now. This one itself, right? Okay, so you okay, so now you imagine that there's this wavefront. You understood that a wavefront will be created, right? Okay, so now you are standing here, okay, and this wavefront is moving forward, so you will also move forward. So what will you see? What will you see then? How can you see the wavefront moving? If you are moving with the wavefront is going to be stationary with respect to you, right? So now instead of moving, right, the stationary things will appear moving. So this gas, which was supposed to be stationary, now that you are moving towards this, so with respect to you, this stationary gas is actually moving towards you with speed c, right? And all those particles which were on this wavefront are also moving. Okay, but between the piston and the wavefront, see, from the stationary frame of reference, what was the speed of these gas particles? So no, the gas particles themselves will move. They will themselves move. Yeah, exactly. So around their place. So let me explain this more clearly. See, between this piston and wavefront, let us consider one particle. Okay, this particle, it is being pushed by some neighboring particle. So every particle is going to move slightly by some speed dv. Right, the piston itself will move with speed v, and all the particles which are very very close to this piston will move with some speed v, and they'll push the neighboring particles, which will again push the neighboring particles, and so on, and that will create a wavefront, and this wavefront is going to travel at a speed c. What is a wavefront? It is not particles. Wavefront is what is a wavefront? Define for me. How do you define a wave? Yeah, it is a perturbation which is traveling, right? So first, what will happen? The wavefront was here. So let us say first the wavefront came here. So all these particles were at that point of time moving with speed c. Then when this perturbation traveled further, these particles have now relaxed to a lower speed. Okay, it is a local speed. So each particle is going to have its local motion. What you have to see is the wavefront. So if I start moving at some speed c, and now I look at this wavefront, it is going to travel towards me, isn't it? Okay, I think I'm confusing you. Let us call this speed A. So this person is moving with speed A. Huh. So then this wavefront is coming forward with speed C. So what will this person see? A minus C, right? And piston will be A minus V. Okay, so that is what we have drawn over here. And A is in the in this direction. So A minus C is what what this person will see moving away. So that is why you have a negative slope. Okay. Now did you understand the stationary gas analysis? Okay, then I'll move forward. Okay, so we know what is static and stagnation quantities also, right? Do you have any specific doubts about stagnation and static quantities? No? Okay. So you must have seen the steady flow energy equation, right? So can you tell me what is the steady flow energy equation? Just energy conservation equation. Okay, so what you have given me is this u square by 2 plus h, which is the enthalpy, plus potential. So we will ignore potential right now. Okay, so then if I am adding any heat plus q, and let us say this is at state 1, so h1 and u1, and this is equal to h2 plus u2 square by 2 plus any work output, right? Okay, so now if we do not have any work output or input, or no heat is added, so if q is 0 and if work output is 0, then we have this h1 plus u1 square by 2 is constant basically, right? So this is conserved. What is this quantity? H plus u square by 2. So right now we discussed that if we have this static flow, we can imagine, this is an imaginary process. I want you to be very careful about this. So imaginary process is that I am going to isentropically bring this flow. Let us say my frame of reference is stationary, so I am going to bring this to a stationary flow, right? And it is going to be isentropic. So we call this as stagnation state, right? So when I do that, there is some enthalpy, original enthalpy H, which is the energy, U relative. Okay, thank you. And then you have also changed that kinetic energy into the enthalpy, right? So this H plus u square by 2 is nothing but stagnation enthalpy, H naught. So I'll denote it by H naught, okay? Okay, so now you must have seen different forms of the energy equation. Let me just add a page here. So you must have seen these different forms. One is that H naught is equal to H plus u square by 2. Then another one is CPT plus u square by 2, right? So this is obvious because H is equal to CPT. So I'm just deriving this so that we are familiar with all these equations. You can write Cp as gamma r by gamma minus 1. Yeah. And then you have this T plus u square by 2. So what is gamma RT? A square. Right, so I can just take that A square out. Okay, A square by gamma minus 1 plus u square by 2. And another thing is RT is nothing but P by rho. So gamma by gamma minus 1 into P by rho plus u square by 2. So these are the equations which have been already discussed in your lectures, right? Also, you must be aware of these equations. T naught related to T. What is it? T naught is T times. Well, you should be yes, 1 plus gamma minus 1 by 2 m square. Okay, and last time we, if you remember, we discussed this PV power gamma is constant and so on. So now, if you notice, we have said that stagnation state will be achieved isentropically. So all the isentropic relations will be valid between the static and stagnation quantities. So if I have to relate, say, the pressure, static pressure and the stagnation pressure, I can relate that by considering the ratio of the static temperature and stagnation temperature, right? Because because we are just using an isentropic process. So what is the relation? Yes, so this is, so you also have this relation that P naught goes like P into 1 plus gamma minus 1 by 2 m square whole to the power of gamma by gamma minus 1, right? Okay, so you also must be aware of the concept of adiabatic ellipse. Yeah, so can you help me with the equation? Okay, just adiabatic ellipse. Yeah, u by u max the whole square plus a naught square as well. Yeah, so can you tell me the formula of u max? What is u max? What is the definition of u max here? Okay. The entire energy has gone to kinetic energy of the gas, and that will happen when, yeah, so when the random motion of the gas molecules becomes 0, then we can say that the static temperature of the gas has become 0, right? And then you can, right. So what is the formula for u max? Do you remember? To gamma r T naught by gamma minus 1, and the derivation is very simple because you just have to put T equal to 0 in your equation. So you have this equation, right? T naught is equal to T plus gamma minus 1 by 2 gamma r u square. So you can get, if T is 0, u max will be here, and T naught is the stagnation temperature of the gas. Okay. Okay, and then what is A naught? Yeah, what is A naught? It's very simple, right? Yeah, so it is speed of sound defined at the stagnation temperature. So it's nothing but gamma r T naught under rho. Okay. You must have also seen the something called the characteristic speed of sound. What is characteristic speed of sound? Okay, so you are going to bring the flow to a hypothetical state of m equal to 1. So that will be called the characteristic speed of sound. Let us call it u star. So how do we obtain u star now? Again, we'll go back to this equation, and over here we'll put Mach equal to 1. If Mach is equal to 1, we have u is equal to a, right, which is nothing but gamma r T under rho. So if you put this into your equation, what do you get? Should I derive it, or you know the derivation? You have the derivation. So what is the, yes, someone is saying something. Okay. Yeah, Mach number is equal to 1. Where is another Mach number coming? Okay. No, it is, there is no Mach m over here, no, because if you see this formula, so even if you were to go back and use this formula, you just have put m equal to 1, right? Yeah, so there is no other Mach number coming. Mach number has been fixed to 1, that is by definition. Okay, let me use that formula then, if you are getting confused. So let us say T naught is equal to T, I'll call this T star, okay, when Mach has become 1. So in that formula we will have to put 1 plus gamma minus 1 by 2 into 1 square, right? So this is what T star into gamma plus 1 by 2. But what is T star? T star is nothing but u square is equal to gamma r T star, right? So you can just replace this. T naught is equal to u square by gamma r into gamma plus 1 by 2. So now if you rearrange, what do you get? This is u star, right? So u star square is 2 gamma r T naught by gamma plus 1. So this is the formula that you would get even if you were to derive it the way it is in lectures, right? So what you said, that if we put Mach as 1, there's no other Mach number coming here. Is it clear? Yeah. Okay, so any doubts about these quantities? Anything at all? Can you repeat your question? No. So, no. This is relative to your frame of reference. But see, there is a difference in characteristic speed of sound and stagnation system. So here I have not assumed any stagnation relation, right? Yeah, but one way of also defining stagnation quantities, sometimes in some textbooks you will see, they say that if I bring the flow isentropically to the character speed of sound, but that is another reference state. It is not stagnation reference state. It is called the characteristic reference state or the star reference state. Okay, so this concept is very important. Right now, we have just assumed that what happens if Mach is 1? Then we have some characteristic speed of the flow depending on the stagnation temperature. Okay, so now if I see, you had some flow, you had some fluid which had some static quantities which is not going to change irrespective of the frame of reference. So now I am going to say, let us have a frame of reference, and according to this frame of reference, let me bring this flow to stagnation, right? So then I have a stagnation reference state. This you are this you know very well. Now let me say that I am going to bring this flow according to the same frame of reference. I am going to bring this flow to the speed of u star, which is nothing but what we got when we put Mach equal to 1. Okay, so this is called the star reference state, and this also we have to bring isentropically, and this state will become very important when we start dealing with shocks and fans. So you learn all these things. So when you start dealing with those shock states, see, shock is a non-isentropic phenomenon. So what we do is we imagine that what if that state was achieved isentropically. So then we need a reference state in the supersonic regime, and that is your star reference state. Okay. Okay. So you know the adiabatic ellipse also. And you know how to derive all the stagnation relations. Okay, so let us discuss one more simple concept, which is wave fronts. Maybe I should have started with this. So how are wave fronts created? So let us say you have this acoustic source over here, okay, and it is stationary. So then it is going to create sound, and that perturbation is going to travel, okay, and after some time what will happen is that this perturbation would have traveled even further, right? So this is going to look like concentric circles. I hope you know this concept. Yeah, okay. And what happens if this source starts traveling with some speed? Let us say that speed is lesser than the speed of sound. Then let us say we had this wave, and this was the source. So when at the next time instant, what will happen is that this source would have traveled this much distance, but since the speed of the source is lesser and the speed of the wave is more, the wave would have traveled much more, right? So always this source is going to remain inside the wavefront. But the moment, so here I have the speed of the source Vs is less than the speed of sound C. But the moment you have Vs more than C, what happens is that the source would have traveled a larger distance, and in the same time the wavefront which was generated at the initial time instant would have only traveled so much distance, right? So that means this source has moved forward and the wavefront is still left behind. This is understood, right? Okay. So this concept is very important, because what this implies is that the source will travel faster than the perturbation. So the perturbations are going to come is not known in many parts of the flow. Okay, and that is what creates shocks in some cases. Okay, so we'll start solving questions if you don't have any conceptual doubts. Any specific questions? No? Okay. Okay, so I have these questions. Now, I'm having the quantities in Rankine or pounds. So you can feel free to use Google or calculators to do the conversion. Okay. So the question says that, so here's a figure of a turbine. You know what is a turbine? Yeah, can you just define what is a turbine? It generates power from the flow. Basically what happens is that, see, these turbines, they have some blades inside, okay, and the flow is going to come, it is going to and these blades are attached to a shaft, right? So the flow is going to gush against these blades and it is going to turn the shaft and create work, right? So the flow energy is going to be transferred to work energy. That is what happens inside a turbine. So here is the question. The entrance temperature is given to you. Okay, so what is given? T1, and the rate at which this flow enters is also given to you. Then the air expands through a pressure ratio of 50. So that means you are given a ratio of P1 versus P2. So what happens in a turbine? Pressure increases or decreases? Decreases. So P1 by P2 is given to you as 50, and then the temperature at which it leaves is also given to you, T2. So the velocities entering and leaving are negligible. So let us assume that the speeds are almost zero, right? And there is no heat transfer. So heat transfer actually occurs in turbine. A lot of heat transfer occurs, but we are going to assume there is no heat transfer. So you have to calculate the horsepower output of the turbine. So how will you proceed? We can consider this as an adiameter. Sorry, can you repeat? Change in enthalpy would be work done. Yeah, so what is the first thing that comes to your mind after seeing this question? What is the question asking you? It is talking about work, energy. So we have to go to the standard steady flow energy equation, which we have discussed over here, right? So this is the equation that we have to use. And they have already told that heat input is negligible. So we just have to equate the change in the enthalpy to the work output, right? So the equation that you will use is H1 plus V1 square by 2 is equal to H2 plus V2 square by 2 plus work. Yeah. So let us call this just W for work. And they have also asked us to neglect V1 and V2. So this is 0, this is 0, and the heat is 0. Okay, so work is nothing but H1 minus H2. Okay, then what do? We can also write H as what? CPT. So this is CP to T1 minus T2. Now we are assuming that CP is not changing in the turbine, which is a fair assumption. Yeah. So how do you convert degree Rankine to Kelvin? Okay, so it's something like a factor of 9 by 5, I think. Yeah, it's 1.8 times Kelvin. So if I want it in Kelvin, I'll just say 2200 divided by 1.8 Kelvin is T1. Okay. So what you're telling me the answer for? 1000? Okay. No, I think I'll just do one thing. I'll give you CP in the units which is used here, which is pounds. So in this FPS units. Yeah, so in the FPS units, CP is 0.24. Yes. Yeah, so that is most of the questions that I'm having are in the FPS units. Okay, so the work you can find over here, which is CP delta T. And how do you find the power? So they have asked you to calculate horsepower, right? Yes. No, so in this equation, in the SFE equation, these are per unit mass, right? Okay, smaller, it just depends on how you write it. So you have to multiply this with m dot, and that will give you the power. So m into w gives you the total work, and per unit time, that is power. Okay, so I'll give you the answers here. This is 266. Right, that is if you are doing it in the SI units. Yeah, yeah. Okay, so I guess the method is more important. So I'll just give you these values, and I request you to do the conversions and check that you're getting these answers. Okay. Okay, but the concept is clear, right? Okay, so we'll move to the next question. Alright, so here there's a pipe, like you can see. The water is flowing in, and the initial diameter is given to you. It is 6-inch duct, and the velocity is given, and within a short distance the duct converges to 3-inch diameter. So what you have to do is you have to find the pressure change, and you have to assume there are no losses. So how do you do this? Continuity equation. What will you use? Continuity equation. How will that give you the pressure? Yeah, that's right. Yeah, so can you give me the equations now? So first we'll start with the continuity. Rho 1 A1 V1 is equal to rho 2 A2 V2, right? So will you take density as constant or not? Yeah, we have to assume density is constant, so I'll just let rho 1 equal to rho 2. So what is V2? V2 is A1 V1 by A2, which is nothing but, so I have the ratio of the diameters, right, which is 6 by 3, so it has to be a square into velocity V1. So what do you get? What is V2? Right, it's 60 feet per second. Then what is the next thing you said you'll do? Bernoulli. No, we don't. No, so we have to find the pressure change. Right, so we need to find delta P. So we don't need the initial pressure.
Okay, I found this on the web for you to have a
Okay, my Siri starts speaking in between. Sorry. Yeah, so what is the Bernoulli equation that you are going to use? P1 by what? Acha, rho G. Yeah. Okay, I can also just write P1 by. Yeah, just do the calculation and tell me the answer. So I can write this as P1 by rho. Yes, so what is delta P? So rho 1 and rho 2 are same, so we can take rho as common into V2 square minus V1 square. Sorry? No, but then I have written V1 square by 2, right? Otherwise it will be 15.98 Pascal. So you have converted. How did you find rho? Wait. You have to find that, right? Yeah, sure. Okay, so I'll give you rho here because I think the question assumes you will find rho. No, they've given it's water. Yeah. You can take 1000 kilograms per meter cube, or you can take this in FPS also. So I'll give you the calculation here. Please. Yeah. It is. Yeah, gravity is 32.2 and density is 62.4 in FPS units. No, so the examples that I'm having are in FPS units. .3 ampere. Yes, yes. But into 10 power 3, right? Okay. Yes. It can be in any units. Mostly they give it in SI units. Yeah, but see, the main thing is these equations is what you have to be careful about. That you should know how to apply. Okay. Any doubts? Anything else? You can also ask that also. Oh, okay. So I cannot give you answers for assignments. You are supposed to solve them on your own. Okay. Okay, so maybe I'll finish the questions that I have and then you can tell me that question. Okay, so the next question is this. At a point in the flow over an F-15 high performance fighter airplane, the pressure, temperature and Mach number are given to you. Okay, so at this point you have to calculate T0, P0, T star and P star and the flow velocity. How will you approach? So the Mach number is given to you, 1.5. So what is given? The pressure and temperature that is given, it is what? Static or stagnation? Read the question carefully and tell me. Okay, because stagnation is being asked. Okay, so see, they are saying at a point in the flow, right? So at any point in the flow they have given, and they are not talking about any frame of reference. So this must be static, isn't it? Okay, so what is given to us is temperature and pressure, which is static. Okay, and now what have they asked is T0, P0 and T star, P star. What is T0, P0? The stagnation quantities, right? And T star, P stars are the star reference quantities. Okay, so how will you answer this question? Yeah, or we can use this form, the equation that T0 is equal to T into 1 plus gamma minus 1 by 2 m square, and yeah, same thing. And now what will you do? You'll just put Mach number equal to 1.5, isn't it? So tell me, what is T0 by T? Sorry, 1.25. No, can you check your calculations? Gamma we'll take for air. Yeah, 1.4. You meant P0 by P is? Yeah, it is 1.45. Who did not get the answer? What were you doing? Did you put m equal to 1.5? Square. Okay. Yeah, you should be careful. Now what is P0 by P? So you know T0 by T. P0 by P is easy to find. Right. So I have just put T0 by T to the power gamma by gamma minus 1. So once you know the temperature ratios, you can find the pressure ratios from that itself. Right? 7, is this what it? Yeah, okay. Okay, and now how do you find these star quantities? So once you know the ratios and they have given you these static quantities, so you just have to multiply the static quantities and get stagnation, right? So T naught will turn out to be 652.5 rand per, and P naught turns out to be 6938 pounds per feet square. Okay. So now you have to tell these star quantities, T star and P star. So what was star reference state? We discussed this. 3663. Yeah, you're very close. So how did you do this? How did you solve? In which equation? What is the equation I should write? P naught is equal to P into 1 plus 1 by 2. Okay, so here I'll put Mach equal to 1. If I put Mach equal to 1, then P becomes P star. So you have to find P star, and you already know P naught, right? Is this how you did it, or did you use the gas tables? No, okay. Yeah, so can you tell me what is the value of P naught by P star? Did the others also get this? Did you understand how to find these ratios? What is T naught by T star? Yeah. So in the top, see what was given to me. This is the actual Mach number of the flow, right? Yeah, so over here first we used Mach as 1.5. We know the static quantity, so we found the stagnation quantity. Now stagnation quantity is my reference quantity, so using that as my reference, so I know the stagnation quantity, and now I assume if the Mach was 1, then what I would get would be the star reference state, right? So what have we done? We first took the flow, so you had this flow, you took it to stagnation, and from stagnation you have taken it to star. That is how you have found the star quantities. Okay. Okay, so can you also please tell me the value of T naught by T star? Again you have to do the same thing. T naught is T star into 1.2. Okay, yeah, that's right. I hope everyone got this. Any doubts in this question? Okay, got it. Everyone got the answer, right? Okay, so I'll give you another question. Just have one more question. So let us consider hydrogen. Okay. So the questions that I have are in FPS. Okay, let me see. Yeah, so okay, I have it in degrees Celsius. I'll give you it in degrees Celsius. So hydrogen, let us say it has a static temperature, T static is 25 degrees Celsius. Okay. So and we are also given that stagnation temperature is 250 degrees Celsius. So can you tell me the Mach number? you can take gamma to be 1.4. So again it's the same formula. So we are given the temperatures in degrees Celsius, right? So we have to convert it to Kelvin. Mach number is 1.94. Yes, it's 1.92 actually. Okay. Yeah, you have to convert it to Kelvin, right? That is very important because you might usually it's coming 1.92. It won't be 1.94. Yes. Mach number is for the flow, which is, so that is from the lab frame of reference, or what you would call from the lecture notes as moving gas analysis. So is this clear? Everything? Yeah, okay, now you can give me your questions. Okay, let me do one thing. Let me write down so you have some question down. Yeah. You are given molecular weight. Cp by Cv is given, which is gamma. Yeah. Combustion pressure. Okay. Combustion pressure is something. Okay, 2580. Yeah. Okay. 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 R. Yeah. Okay. 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 So you want me to tell you how to approach, right? I'll not tell you the solution. Okay. Okay, so how you would approach this is, first of all, the most important piece of information that is given to you is that the flow is isentropic. So what does that imply? If it is isentropic, then I can find a reference state, the stagnation state, which is going to be same throughout, isn't it? Yeah, so now you are given the exit pressure, and where is the combustion happening? Is that given? It must be before the nozzle, right? Yeah, so it is in this combustion chamber. In the combustion chamber, you are given the pressure, the temperature, and then you allow this flow to move through the nozzle. So then I can consider this combustion pressure as my stagnation quantity, and the stagnation temperature also will be equal to the temperature in the combustion chamber. So the assumption here is that there is no flow, and after combustion it starts flowing in the CD nozzle. Okay, so these are my stagnation quantities, and now I have a static quantity at the exit. So the moment I have a static quantity, I can find the Mach number, right? And yeah, so yeah, so you will get this exit Mach number. Is that clear? Yes. See, the stagnation quantity is a reference, right? And that reference stays. See, I'll tell you something. So first, let us assume there is a any flow, any channel flow, and if I have assumed that from this point A to this point B, the flow is isentropic, okay, then whatever is the stagnation over here, stagnation quantity, so stagnation at A is going to stay same at B also, right? But if I have a shock over here, then there is a loss. So you will have some losses across the shock, and then that is also known as stagnation losses. Okay, so then your stagnation quantity will not remain the same. Now in this CD nozzle, they have given that the flow is isentropic, isn't it? Yeah, so then you will not have any losses in this nozzle, and that is why whatever stagnation quantity you have obtained in the combustion chamber, that is going to remain up till the exit. Okay. Okay, so now what did you do? You had P naught and you had P exit, so you can find M exit. Now the moment you have M exit and you also had T naught, so using T naught and M exit, you can find T exit. Yeah. What was P naught? P naught was equal to your pressure in the combustion chamber, which is given, right? And P exit also you said is given. No, that is fine. I mean, those are values. I'm just telling you the method. Yeah, so the one who was asking the question, I cannot see your faces right now because of the sharing screen. Okay, so I think what you're not understanding is why we are taking this combustion chamber pressure as stagnation. Okay, so you have to, because see, in the combustion chamber we assume that there is no flow. So let us say there was some flow, then what would be stagnation? When you bring that flow to zero, right? Exactly. But in combustion chamber there is no flow, so that is why whatever is given is the stagnation pressure, and what is given in the temperature is also, that is the stagnation temperature. Correct. So now you understood how to find all these quantities, right? So then so now you have T naught, then you have exit Mach numbers, you can find the exit temperature, and you can also find by the area Mach relation you can get the exit area, right? Yeah, velocity at exit can be found because you know T exit. You know how to find m dot and AE, so you would have some function. Yeah, you have a formula which relates the mass flow rate to Mach number, right? And you would have area related to the throat area and to the Mach number, right? So you can find m dot and a from those formula. Okay. Yeah, it will be constant. So how will you find it? But what are the quantities which you know which you will use? Yeah. Yeah. So either it is a function of Mach number or it would be in terms of the stagnation temperature or stagnation pressure. So you can find the mass flow rate. Okay, so you have so you are watching lectures of week 3 now. Week 4. Yeah, so from my understanding, we are holding these tutorials then by 1 week late, I think. So we started 1 week late so that you can cover up your lectures. Okay, because I'll be discussing these questions in the next session. These kind of questions. Right now, whatever I discussed was mostly static, stagnation, and adiabatic ellipse. So all this was in week 2. This is week 2 tutorial. Okay. 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 Any other questions? Area Mach relation. So you want me to derive them? Yeah, there's a huge formula. Yeah. Okay, so why don't you do this? You can show that to me next time. Yeah. Okay. I don't use LinkedIn. Yeah. But you will have my email ID, right? So I can even tell you here. No, I'm sorry, I'm not allowed to do that. Yeah, so you can email me. This is my email ID. Okay. Questions related to the topic. We can discuss all this later. Yeah, they'll be available. So last time I was not able to upload because the file was too heavy, but I'll do that now. It will be on YouTube. No, only my voice. Okay, so if you have no more doubts, then I'll discuss one concept which I think is really important. So, the book that I referred to you last time, Zucker and Viblas, did you guys go and have a look at that? No, that's okay, but did you see this book, Zucker and Viblas? Okay. Oh, you can download it, download a PDF, right? Okay, so what I'll do is I have the PDF, and there is one folder which you will be referring to. Like, I will be uploading these notes in that folder, right? So I'll upload the book also. So you must be having this link. Okay, I'll show you after the class. There's a link where you can access all the recordings and the notes. You should go on the page, the website of the course, and see over there. If it's not available, just let me know. Next time I'll contact the authorities and ask them to make the links available. Okay, so like we had this steady flow energy equation, right? We also have something called the stagnation pressure energy equation. Have you heard of this? Okay, so you can just note the equation. I'll not show the derivation, but I'll basically explain you the funda behind this. Stagnation pressure energy equation, and we are assuming one dimensional steady flow and so on. So the equation turns out to be like this: dP naught by rho naught. Naught denotes the stagnation quantities as usual, plus ds. ds is entropy, okay, into T naught minus T, and let us say this is isentropic. So, okay, let me first write this. The entropy itself can be split into two quantities, dSe plus dSi. This is all due to the reversible processes, and this is all due to the irreversible processes. Okay. So the equation, I'm continuing writing the equation. dSi is the irreversible part of the change in entropy, plus delta W is 0. Okay, so this is the stagnation pressure energy equation. Have you seen this before? No. Okay, so what this equation says, if you see very carefully, it is relating the stagnation quantities. Okay, so the first thing is any change in the stagnation pressure related to the stagnation density, right? So this is a change in the stagnation pressure. So like we discussed this question over here, and you asked why the stagnation pressure which is in the combustion chamber is going to remain the same at the exit.
I didn't get that. Could you try again?
Right, so why will that be? Because the flow in this CD nozzle was isentropic, no irreversibilities. So if I go to this equation, the irreversibility was 0 and there was no work being added, and also there is no temperature change. Now if there was some sudden heat added in the CD nozzle, then the assumption that we made is not going to hold true. Are you understanding? Yeah. A star, why would that be same throughout? No, I'm talking about right now. I'm talking about the stagnation quantities. The star quantities are not. I'm sorry, I did not understand. So you're saying that A star is going to remain same here? Okay, that is fine. Yeah, but that is not related to this equation in any way. This equation just says, yeah, so this equation just says that there will be a change in the stagnation pressure head only when there is some irreversibility or some work added, or there is some change in the entropy due to the reversible processes, or there is this T naught minus T differences there, right? So these are the reasons, these three reasons, so 1, 2 and 3, these three reasons will change the stagnation pressure. Now why this is important? Because see, the moment you have a shock, there is an irreversibility. So the stagnation pressure is going to change across a shock. Are you understanding this? If there is a turbine, there is work being extracted. If there is a compressor, work is being added. So again, the stagnation pressure should change. If combustion is happening, there is heat being added, then the stagnation pressure should ideally change. Understood? So when you read propulsion, you have a compressor, turbine, and in between the compressor and turbine you have a combustion chamber, right? So in the compressor, the flow comes in, there is work being added to the flow to compress it, so there is delta W. So that is why the stagnation pressure should change in the compressor. Similarly, in the turbine, the flow energy is converted to work energy, right? So here also the stagnation pressure changes. Now in the combustion chamber, if you see most of the books, they say that the stagnation pressure remains constant. That is only by assumption. Ideally, in a combustion chamber, the stagnation pressure is going to change and it is going to decrease. Understood? Is this concept clear? Why would it decrease? Because there are losses, right? So what happens in a combustion chamber? You are adding energy. Okay, so when you add energy, stagnation temperature increases, static temperature also increases. Yes, why should the stagnation pressure decrease? Is because stagnation pressure will increase only when work is being added to the system, not when heat is being added. Okay, yeah, definitely. Okay, so what you can also derive from this equation, after some massaging of the equation, you can get this equation: P02 by P01 is equal to e to the power of minus delta S by R. R is your universal gas constant. Delta S is the change in entropy, okay, and that is going to reflect in the change in pressure loss. So this answers your question pretty much. Entropy always increases, okay, especially for a closed system. Entropy is going to increase, so then stagnation pressure is going to decrease. Do you understand? Yeah. So what happens in a combustion chamber is that entropy is going to increase because you are adding heat to the system, and that is why your stagnation pressure is supposed to decrease. Okay. So I have one more question. If you want, we do have time. We have time. So I'll give you the question, but again, this is in FPS system. Okay, so I don't have the question typed here, so let me write it down. So let us consider oxygen flowing in a constant area duct. Okay, so O2 flows in constant area duct. And the duct is horizontal and it is insulated, so assume there are no losses. Okay. And let us say we are so I'll just draw this duct for you. Okay. and this is section 1, which is the inlet, and at the inlet we are given P1, T1 and V1. V1 is the speed, so P1 is given to be 50 pounds per square inch area. Okay, T1 is given to be 600 degree Rankine, and V1 is given to be 2860 feet per second. And at the downstream section, let us say over here at section 2, what is given is T2, which is 1048 degree Rankine. So temperature has increased. So now the question is,
I didn't catch that. Could you try again?
okay, so now the question part 1 is, you have to find M1, T01. The other things you have to find is V2, P2, and you have to find what is the change in the entropy. So change in entropy between section 1 and 2. So how will you proceed? Yeah, I can give you, yeah. So I can give you this value. So you'll apply this formula A into gamma R T rate. You can take it as 32.2 into 48.2. There's a conversion factor which will come. So this R into GC is what I've given you. So maybe instead of discussing the exact values, you can tell me how you will proceed. So Mach number will be M is equal to V1 by A1. No. So A1 is equal to under root gamma R T1, right? Yeah, and T1 is known, so you can find A1, and V1 is known, so you can find M1. Fine. Then you will have to find T01. T01 is equal to T1 into 1 plus gamma minus 1 by 2 M1 square. Now M1 is known, T1 is known, so you can find T0. Is that fine? Yeah, okay. So now you can tell me the values. What is A1? This is supposed to be 1.4 into 600 into so what is the value of A1 in feet per second? Are you calculating? Yeah, so it's approximately 1143 feet per second. And what is T0 value? T01. you can keep it in Rankine itself. T1 is known in 600 degree Rankine. So what is M1 first? Yeah, the given is V1 by A1. Yeah, so you know V1. So now you can just calculate M1 and L1. V1 is 2860. 2860. T01 is no, first tell me Mach value. What is Mach value? M1. Yeah, 2.5. Then why are you not getting T0? So the 1351.3, yeah. So it's approximately 1351 degree. Okay, so I think everyone is making the same mistake. You're not putting M square. You should be very careful. Okay, so what will you do next? We have to find V2 and P2. So now we know the Mach number at 1. We know the stagnation temperature. Fine. What is the main property of the flow between 1 and 2? It is isentropy. There are no losses. So how will you proceed? And it is a constant area term. Mass flow rate equation. Okay, so what will you write? Continuity equation. What will it be? Rho 1 A1 V1, rho 2 A2 V2. But A1 is equal to A2, so I'll just cancel it. And how will you find rho 1 and rho 2? You can use equation of state. P is equal to rho RT. So I can say rho 1 is P1 by T1. And R will get cancelled on both sides anyways. Okay, so I know T1, T2. I have to find P1 and P2 then. How do you proceed? Yeah, any idea, anyone? Okay, so look at the question carefully. What does it say? There are no losses. So what will you apply? Energy equation can be applied. What will that be? Yeah, so it's just H01 is equal to H02 is right, because there's no heat added, there's no work. Okay, so that also means T01 is equal to T02, but T01 we just found out earlier, so we know T02, and we are also given T2. So this is T2 into 1 plus gamma minus 1 by 2 M2 square. So we know T02, we know T2. What do we need to find? M2. So calculate M2 and tell me. So I'll write the values here for your convenience. T02, which is also equal to T01, is 1350, and T2 is given to us 1048. Okay, this is 1351, right? Yeah, M2 is 1.2. Okay. Then what will you do? Once you know M2 and you know T2, what can you find? What do we need? We need V2 and P2. So if you go to continuity equation, see, you know V1, P1, T1, but you don't know V2 and you don't know P2. There are two unknown quantities, but you know M2, and M2 is equal to V2 by A2, which is V2 by under root gamma R T2. So you can find V2, right? Okay. So yeah, just go ahead and find it. No, so yeah, the value is what I gave you earlier in 32.2 into 48.3 is what we take. Okay, 1812 feet per second. Okay, so now what do we do? Do you know P1? How do you find P1? P1 is given to you. It's 15 psi. Okay, so now you can apply your continuity equation and get P2. This is clear, right? I've just rearranged the continuity equation from here. Yeah, so we just need to find this quantity, right? So P2 is going to be V1 by V2 into T2 by T1 into P1. So I've written here. So you can find the answer and tell me. P1 is 50. So what is the answer you're getting? 137.85. Okay, so then there's another part of the question, which is you have to find a delta S. So first of all, why is there a change in entropy? When will there be a change in entropy? Not necessarily. You need not add heat. Yeah, there can be any type of irreversibility. So in any case, this is the formula that we have to use. If there is a change in the stagnation pressure loss, that will reflect as the entropy, right? So we know all the quantities at station 1 and 2, and we have assumed that there are no losses due to friction, but there could be some other type of losses, right? Oh, sorry, there are no losses due to heat. No losses due to heat because the pipe itself is insulated. But there could be losses due to friction. Okay, so what will you do? You know P1, you know M1, you will have to find P01. Okay, so find P01, find P02, and then find delta S. Do you want me to give any values here? So you remember M1 was 2.5, P1 was 50. So what is P01? But there is no shock, right? No, we cannot use. See, if the change in the Mach number happens because of a shock, then you can use that for. Yeah, so what is P01 that you get? Yes. It is assumed to be isentropic, but no, in the question it is not given isentropic. You can use isentropic relations only because there is no, you can use adiabatic relations because there is no heat loss or heat addition. Okay, so if you see carefully, what the question says is that there are no constant, it is a constant area duct and there are no losses because the pipe is insulated. Right, so those are adiabatic relations, right? Yeah, but the relations you are using are adiabatic. So what is the question here? Can we use stagnation quantities or not? Okay, so if if I was assuming an isentropic flow, then the stagnation quantities at 1 will be the same as stagnation quantities at 2, right? But that is not happening, which means the flow has not remained isentropic. So what you are doing, you are going into station 1, you are taking the static flow and isentropically converting it to stagnation. Then you are going to station 2 independently and converting those static conditions to some stagnation conditions. Yeah. So what is the value of P01 that you get? 854. Similarly, you have to calculate P02. So M2, you know, what was M2? 1.2, right? And P2 you just found up here. So what is P02? Are you calculating? Mm, 3220, that is very high. See, M1 was 2.5, then your P naught was some 800. Now Mach number is decreased, no? Three, three, four. Yeah, that's right. Okay. So now what you can do is you can simply use that formula. P naught 2 by P naught 1 is equal to e to the power of minus delta S by R, and R is your R gas. So if you just plug in the values, you can find delta S, and P naught 2 by P naught 1 is less than 1, right? This quantity, because P naught 2 is lesser than P naught 1, this is less than 1. So when you take the logarithmic, there will be a negative sign which will get cancelled, and delta S value will be, so in FPS units I am writing the value here, 0.058, but depending on whatever units you are using. Okay, but here see, there is a difference. Okay, the formula, which formula you are talking about is this one, right? Yeah, but see, for a shock this is the formula, but what I was trying to point out is this P naught 2 by P naught 1 you have to get by considering the quantities, static quantities over here, isn't it, which are given. In the case of a shock, what you will do is you will have a shock, and across the shock you will know the stagnation pressure losses based on the Mach number across the shock, isn't it? So you will be given a shock and you have M1 and M2, and accordingly you will have P naught 1 and P naught 2. So that will be a different case. There is no shock over here. Yeah, and for the shock also the formula comes exactly from this stagnation pressure energy equation. So the formula is going to remain the same. Okay. 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 Yeah, I should remember almost all. Anyways, this is online, right? So I mean, you can always have the formula list in front of you, isn't it? Yeah. Okay. Oh, okay. I'm not aware about what formula they'll give you, but usually in our college we are given the liberty to see the formula. Yeah, the questions are definitely tough. So I want you to please go and look into this stagnation pressure energy equation and read about it, because this is the most conceptual thing. One is the standard, the steady flow energy equation, and one is this pressure energy equation. Are there any questions? No questions. Okay. Okay, so that's all I have for today. Stop recording. Thank you, everyone.